So recall that a roller coaster car moving without friction along a curve exhibits the conservation of mechanical energy. So using the conservation of mechanical energy concept, we want to find A, the velocity of a 1,000 kilogram car at the bottom of a 40-meter curve, and B, we want to find the height of our moving car at which it will have exactly half the velocity as in part A. So let's begin with part A. So let's suppose our top, or at the top of our curve, our car has no velocity. So that means it only has gravitational potential energy. Let's suppose the height is 40 meters. So we want to calculate what the velocity of our 1,000 kilogram object, the roller coaster car, will have at the bottom of the curve when it will have no gravitational potential energy. So basically we want to find the total mechanical energy, the total energy of the car found at the top. Now the total mechanical energy at the top will be exactly equal to the total mechanical energy found at the bottom. So using that idea, we want to calculate the velocity. So let's begin at the top. What is the total mechanical energy at the top? Well, it's simply the sum of the kinetic energy and the gravitational potential energy. So 1/2 mv1 squared plus mgh1, where h1 is simply 40 meters and v1 is simply 0 because we're assuming the roller coaster car is at rest. So this term goes to 0 and we're left with 1,000 kilograms multiplied by 9.8 meters per second squared multiplied by 40 meters, and we're left with 392,000 joules of mechanical energy found at the top. Now at the bottom it will have the same exact total mechanical energy because only conservative forces are acting on our object. So at the bottom, our E will be exactly the same as before, 392,000 joules. Now, however, the mgh2 is 0. We have no gravitational potential energy at the bottom because the height is 0. Our car is at the bottom of the coaster. So we're only going to have kinetic energy. All the gravitational potential energy stored in the car will be transformed into kinetic energy, the energy of motion. So this value is equal to 1/2 mass v2 squared, where mass is 1,000 kilograms. So we can solve for the v2 and we get our velocity at the bottom. v2 is equal to the square root of 2 times this value divided by the mass, and we get 28 meters per second. So at the bottom of the roller coaster, our velocity of the roller coaster car that has a mass of 1,000 kilograms will be 28 meters per second. Now, what about part 2? We want to calculate the height at which our roller coaster car will have a velocity of half of 28 meters per second, so 14 meters per second. So our car goes all the way to the bottom and then begins to travel back upward. And we want to find the height at which it has a velocity of 14 meters per second. So some of that kinetic energy has now transformed into gravitational potential energy. So once again, we use our mechanical energy equation. The total mechanical energy is equal to 1/2 mv squared plus mgh, where now our velocity is 14 meters per second. Our E is still this value because we have a conservation of mechanical energy. Our mechanical energy remains constant throughout our trip. So we see that E is equal to this value, where E is this number. So we have the V, we have the M, we have the G, we have the M, we don't have the H. That's what we want to find. So we solve for H, we plug in our values. So 392 joules of energy minus the kinetic energy our object has. So the top will give us the total gravitational potential energy we have. We divide that by the mass and the gravitational constant, the product of the mass and the gravitational constant, and we get 30 meters. So, at 30 meters, our car that has a mass of 1,000 kilograms will have a velocity of half of 28 meters per second, or 14 meters per second.